Okay, today we're going to talk about the second part of the fundamental theorem of calculus. We already know the first part of the fundamental theorem of calculus. We learned that before the quiz, and you'll remember it gave us an idea about the relationship between derivatives and integrals. And what we found in the first part of the fundamental theorem of calculus was that if we had some function defined as the integral of another function, then there's a specific relationship between g and f here, and that is that the derivative of g is the same as the unintegrated function f. And this made us begin to realize that derivatives and integrals are inverses. The second part of the fundamental theorem of calculus we'll use to find change in a function, and that will help us then in solving application problems. So let's get our setup here. We can see that f of t is a continuous function on the interval ab with derivative lowercase f of t. Textbooks often use this convention of making a capital the original function and the lowercase the derivative. Just read carefully if you see those two presented in the same problem. I will typically indicate capital F of t and its derivative by using the normal f prime of t. So we talked about the velocity distance problem when we were first being introduced to the definite integral. Here we are going to think about it again. Let s of t represent the position function, that's what we normally do, and v of t is its derivative representing velocity. So we have an original function s of t and its derivative v of t. We want to find the total distance traveled on an interval from a to b. One thing we could do is just, if we knew the function, the position function, we could just subtract the position at time b, subtract the position at time a, and we'd know how far we'd traveled, assuming that distance was all in a positive, the motion was all in a positive direction. We could also deal with velocity, and we saw that when we first started talking about the definite integral. We started with a distance traveled question. You'll remember that velocity in that case was positive and increasing, and we figured out that if we did change in time times a velocity value, that we could predict, at least with some degree of accuracy, the total distance traveled. We now know that we can represent this notion of change in time times velocity, or change in x times a y value, using the definite integral, that those are the same. And since this formula was producing distance traveled for us, and this formula produces distance traveled for us, those two things must be the same. So the integral from a to b of v of t dt must give us change in position. This also represents distance traveled as long as the velocity is positive. We will talk about situations where velocity may be positive or negative, and then what does this indicate to us. But the main idea here is that if I integrate a derivative over a specified interval, then I'm actually finding change in the original function over that interval. So here we have our formal statement of the fundamental theorem of calculus. Here it is in words. The integral of a rate of change function gives us the total change in the original function. When we talk about total change, we mean change in y values. We already know how much the x values change. That's our interval. And so integrating a rate of change gives us the change in amount, or the change in y values. Notice that it doesn't give us the new y value. It only tells us how much increase or decrease has occurred. Here's our formal mathematical statement. If lowercase f is continuous on the interval ab, and lowercase is the derivative of uppercase f, capital F, then the integral from a to b of little f equals the change in the original function f of b minus f of a. We already knew this, that the derivatives and integrals are inverses. They undo each other. This is the bit that's new, at least in terms of an application problem. If we integrate a rate of change function, we get the amount of change in the original function, or the change in y values, how much y increased or decreased in the original function. Let's look at an example. So we're going to find total change from a rate of change function. Here we have capital F of t representing a bacterial population which is 5 million at t is 0. After t hours, the population is growing at a rate of 2 to the t million bacteria per hour. Estimate the total increase in the population, and the total population at t is 2. So let's start taking apart what we know here. In these problems, we will often have a function or some information about the amount of the substance, and then we'll also know something or have some information about the rate of change, or the rate function. So if I read through my given information, I see that f of t is my amount function. Let f of t represent a bacterial population. So the total amount of bacteria present in the population. It goes on to say I have 5 million bacteria at t is 0. So I know that the amount at time 0 is 5 million. In the next sentence, I'm suddenly talking about rate. Suppose that after t hours, the population is growing at a rate of 2 to the t million bacteria per hour. So I have two indications that this is a rate function. They tell me growing at a rate of, and then I also have the units of the function itself, bacteria per hour, and something per something indicates that I have divided, which gives me a derivative function. So I know the derivative of the bacteria population, the growth rate, is 2 to the t. I'm being asked to estimate the total increase in population during the first 2 hours. The fundamental theorem of calculus tells me that if I integrate a rate of change function, I get total amount of change. So I'm going to integrate my rate of change function here from 0 to 2. My rate of change function is 2 to the t, my dt. I'm just using the calculator to integrate that, good old Math 9. I put 2 to the t in y1 and then integrated from 0 to 2, and I get this numerical answer. Remember to round to 3 decimal places. That's standard on the AP Calculus exam, so it'll be standard for us too. Now let's talk about what this number means. That 4.328 is the new bacteria that's been added to the culture since time 0. So 4.328, it's measured in million bacteria between t equals 0 and t equals 2. And I probably should say million new bacteria. So we have new bacteria being added during that time period. Then I'm supposed to estimate the total population at t is 2. Well, in order to do that, I need to know how much I had to start with. So I need to know my original amount, or how much there was at time 0. I need to know how much change occurred, and that will give me my total. So my original amount, I know f of 0 is 5. The total change is given to me by the definite integral. Now I have the total amount of bacteria at time t, million bacteria at t is 2. All right, let's look at